I'm 144 gigabyte array.
Gigabyte. I have a 5.7 gigabyte array.
Yeah, but yours are supposed to be spatters, letters.
Plus the screen is going to get recorded at the same time.
But we want
But as you're pointing
speaker
at
and
it,
in the screen.
I have
Today.
Screen.
It's just the cable that goes
Okay.
All right, very good.
Many thanks.
You're welcome. Unless you do the pair
What I'm going to do is I'm going to start with this stream shape. Start part.
Okay. Many thanks for coming back and not forgetting that we have a class after a week of no class.
and we have a week of no class.
Huh? Well, you may have decided that it is a trend and we do not have class anymore. But we do. Yeah. So today we do have the presentations which complement our fourth chapter in the class. Before we had 3 chapters of time-independent perturbation theory, time-dependent perturbation theory, and angular momentum, is followed by applications or advanced chapters in form of presentation. And recently we went through non-equilibrium, non-linear time-dependent phenomena, starting from the background concepts. And today there is a chance of all class attendees to complement the boring and simple background material by summing blooming and more advanced chapters or applications. So what we do today includes 2 presentations on methods, 2 and 3, and then there will be 3 applications at the end, and there is 1 application at the beginning with the following logic. The presentation number 1 is the only model that in principle can be pursued without advanced methods. It is one of the exactly solvable models that has exact solution without processing time-dependent Hamiltonian and special equations, but it is a good example that helps us to look from different angle on the interacting systems. And then there will be 2 advanced methodology methods and 3 applications of NMR, and it was a lot of interest to quantum computing, so there will be 2 presentations covering from different angles. So all your slides are uploaded to this PC, and they are numbered and labeled according to your name. So 1st, 2nd, 3rd, 4th, 5th, 6th. So if you suddenly forget what to do, you just find number in your name, click, and it does pop up. If you dislike PowerPoint and your presentation is in PDF, you have option either run it in PowerPoint or in PDF. Here. So we should try to finish within like hour plus something. So let's plan on staying no longer than 10 minutes up front. Everyone is invited to please speaker by questions. And with this, I would like to announce the presentation by Javed Abu Mohammed, who will tell us about atom in the cavity electromagnetic field with Jaynes-Cummings model. So try to stay in this area.
Oh, okay. Thank you. And so I'm going to talk on the Jaynes-Cummings model about this one, and especially in the photon cavity, how the two-level system interact with the photon. So if we look on this one is this picture is one of the representation of the cavity system. If we apply the photon, it's going there, and because of when this absorbs some photons, and the number of photons is decreasing here, and again it's emitting, so it's getting, so it's making a cavity here. That's why it's known as a cavity system. And so first Jaynes-Cummings is first analyzed this such two-level system in 1963, and considered that two levels only: ground state and excited state. And then if we consider the other similar system like a Rabi interaction system, they consider that interaction dE by this one only, dE cos omega t. But in these cases, in the Jaynes-Cummings model, they are considered as a photon interaction, as a photon, not as a continuous wave function. So that's why they define the interaction cavity field E with this formula. In these cases, this one is annihilating and creation operator here to make a photon and create an absorbing photon. So now, if we want to make a Hamiltonian for this system, first interaction Hamiltonian is defined by this term, and where D is defined by D1, this is making a dipole, and E is giving you the direction of the dipole things. And atomic transition operator is giving us by this one, can be comparable with the Pauli matrix, Pauli spin matrix. You can compare these two, and so that's why it's giving us these two cumulative. This relation we can get from here, and the dipole operator D is defining by the two state, only ground state and excited state. And finally we will get this one. And so so there are three different effects. One is the interactions with the photon and the two states, and this one is the atomic Hamiltonian, where the atomic energy is defining by this one is from these two as a Pauli matrix, and the free field Hamiltonian will define by this one is annihilation and creation operator of the photon. And then if we add these three terms, we will get this Hamiltonian from these three terms, and this Hamiltonian is known as a Jaynes-Cummings Hamiltonian. So if we want to know the electron dynamics of this one, and if another one is if we solve these two terms, we will get this one, because sigma minus and alpha plus we consider the 0, 1, and alpha plus is sigma plus and alpha is consider another two will be 0, and finally we'll get sigma plus alpha plus sigma minus alpha dagger. And then if we want to calculate the transitions, first we consider another operator. This is called actual number operator, I guess, and it will give us the number of photon in the system. And we want to divide this Hamiltonian, Jaynes Hamiltonian, the two different Hamiltonian, H1b and H1b H2. These two Hamiltonian are defining by this one, H1 and H2, and both one, I mean H1 and H2, both are suddenly I forgot one very common term. They commute, this one, they both are commute with H1 in this research. And if we look, I skipped some mathematical formula. If this one is H1, cannot change the basis of the wave function, it only changes the number of, it also accumulates the phase only. It doesn't accumulate the phase. Accumulation of phase with the time is depends on this Hamiltonian. And so if we want to construct the basis, we will get this basis from the initial state and ground state. We consider this one excited state as the initial state, but this form also can be solvable as a considered ground state as a initial state. So this one is the initial state, and by emitting a photon is going to the ground state. Because of emitting is increasing the one number of photon here. That's why is n plus 1. If we consider the ground state as the initial state, it will go to the excited state and photon number will be n-1, we will get the final state. And this is the linear combination of these two states. And if we put this in the time dependent Schrodinger equations, and then if we solve the equations from here, we will get this one, and then finally we will get two coefficients here, this one and this one, and from these two we get the probability of the electron populations in the ground state and excited states. So this one is the initial state, this one is the final. Initial means is excited state. In our case, the final state is the ground state. This will give you the population in the initial, excited state and final state at time t. Now we want to look on the atomic inversions, the electron transition from ground to excited state to ground state. We can calculate from here and by these equations, and this term is known as a Rabi frequency, this term, and then we can calculate here. And if we plot this one, we will get this symmetrical inversion of these electrons from grounded to excited state. One interesting thing of Jaynes model and Rabi frequency model is when electron going to excited state, if you stop the radiations, that electron wouldn't go down there in the ground state. It will come in the excited state. But in the Jaynes model, if you stop the radiation, it will continue this process. It will emit the photons going to the ground state and absorb the photon again. It will go to the excited state again. So, and now we want to look on this solution in coherent state. So in coherent states, we can define this state by here in the ground state and excited state, and a field by this term. This is a coherent state, the different number of photons with this number. And now in the ground state, the basis we can define by this one is atomic basis and the field basis with the direct multiplication of these two one. And if we solve all of these by putting in the Gaussian and the Schrodinger equations, we will get the in time ground state wave functions, and this one wave function. This depends on these two terms. And from all other maths what we did, and we can calculate the inversion of the atomic inversions of the incoherent state. And if we solve this one, we will get this coherent, inversion functions. And if we plot this one, we will get this type of plots. In its term, this, if we look on this first, it will show the two different states. This one is known as one is variable state, and there are two different names of this state and this state. I just forget this one. And if we continue this propagations for longer time, we will see that the this two state is going closer now here. That means it's almost like in the Rabi system in the longer time. So this is one of the main difference of this Jaynes model and Rabi system. So at the larger number of n, we will get this compact system, and if there is a small number of n, we will get this one. In this case, t is defined by lambda t here, and so we will get this one. So this is the Jaynes system model, and we can, I skip all other derivation, we can get a Jaynes state. Jaynes state means this state can be produce the two discrete states. It depends on the number of n, and we also derive some other factors too from the Jaynes model.
Okay, let's thank Gifford. And questions are very welcome. If there are, yes, please.
You point to the diagram and you say this state and that state. I don't. What's
This one and this one.
Well, on both.
These are same one. Is plotting the WT with the time. So when the shorter time is showing this. I forget the exact name of this. Is it invariation or this, because it's going to the zero here, and then it started to fluctuate again. But with the longer time, this del t is going to smaller and smaller.
Deyan, would you allow me to
I
ask
forgot
some
the
similar
exact
question?
word, so yeah.
So I had the same question in maybe a little different words. Right now, you are showing expectation value of the SZ spin projection, right?
Yeah.
For this two-level system. If you compute other two, how would this dynamic look on the Bloch sphere? Specifically, what will be the length of the Bloch vector, especially at the initial interval of time? Would it stay constant or it will change?
In this case, it will be constant.
Length. Brendan? Would you like to share your opinion and maybe try to help him?
I'm sorry, what was that? I missed the question.
Would you see any connection between this event that Gifford is showing and free induction decay? Would the length of Bloch vector stay constant or decrease?
Probably decrease.
Probably decrease. Okay. More questions to Gifford? So it is a prototypical analog of relaxation, right?
Yeah.
So it comes to 50% of population in ground and excited. On a short, originally,
yeah.
until here,
Yeah.
right? So it is importance and impact of this model. It shows mechanistically how one can shorten the length of the Bloch vector and how one can change the population.
So is the envelope of this function related to the length of the Bloch vector, or
Well, you need
Just the
to compute two other projections. Then it will look a little differently. But it will take.
this is just for SZ?
Yes. Good. More questions? Can you go to slide number 2? Or yes. Here. So you are representing electric field by a summation of these two operators. What do you do? Why? How do you interpret it?
This one is actually, I mean, this one we consider as a photon, as a quantum energy. Is annihilation and creation of photons.
So you
That's
wanted
what-
to say
yeah.
that mode of electromagnetic field is a harmonic oscillator.
Yeah, kind of.
Okay, very good. Let's thank Gifford once again. So the next presentation will be by Aaron Forde with a little more insight into methodology, and he will logically continue this idea. If here in the presentation by Gifford, we were looking on the dynamics of two levels, of this two-level system. But it was affected by interaction with one harmonic oscillator. And we saw that something that looks like relaxation happens. Aaron will try to share his vision and opinion what happens if there will be more than one oscillators, if they have other than photon nature, for example, phonons, and is there any use of so-called autocorrelation function in describing this phenomenon? Floor is yours.
So for my presentation, I'll be talking about how correlation functions are used to get dissipation rates in the density matrix. So essential concept here is, what is a correlation function? So very generally, correlation functions, they describe, it's a measure of like how two variables depend on one another in time. So the easiest, maybe the best explanation is this figure here. So we're multiplying two functions together and we're seeing how it changes in time. So like you can view one stationary and we're moving the other function past it. And then these are just different notations on how the correlation functions show up in different notations. And specifically we'll be using autocorrelation functions for operators.
You mean
The
when
density matrix.
F equals G?
F equals G.
When it is in your first
Right.
definition? When
Right.
there is the same function.
Right, so it's overlapping the same function through time. So that's why it's called an autocorrelation. So it's auto meaning self. So an example here, hopefully this image. So, oops, I meant deposit. So if we go up to, so initially we see that there's two wave packets and they're exactly overlapped. So you'd see a very high peak here, meaning that the multiplying is positive and they're in phase. If we move it across, so we see when we get out of phase, or when we multiply them two together, we get negative peaks here. So they're kind of like negatively correlated. The wave packet moves further, you get another region where they're in phase again, so you get a little positive peak there. Then eventually they just kind of, the other one just drifts by the other one. If you plotted the correlation function for each time step, you'd get a plot that looks like this. So this is the initial state, and this would be when they're out of phase, comes back into phase, and then they just kind of pass towards each other. So that's a visual representation of what the correlation function represents. And then there's an important parameter which we call the correlation time, TC. So that's like the amount of time it takes for the two operators to be not correlated with each other anymore. They're basically independent, which is important because for operators we like them to be move. We want our operators to be independent of one another. So when we do our equations, that we can make them independent of one another, which simplifies the equations quite a bit. So the importance of these autocorrelation functions is that we can describe rates of transitions in terms of correlation functions. So if we consider Fermi's golden rule shown here, if you do a little manipulation where you take the delta function and you expand it as an exponential integral and then you times by a Boltzmann factor, you can rewrite it in terms of correlation function shown here. And it looks kind of weird, but if you look at it and you look at the units, like you can show that it's a rate because you get joules squared times seconds, and then there should be another factor of h bar out here, so you get divided by h bar squared. So you get joules squared seconds divided by joules squared seconds squared, so you get 1 over seconds. So that's why that's a rate. And then we can only use correlation functions under the Markov approximation. So we're not really integrating necessarily here, so we're considering time steps that are bigger than, like, we're talking about discrete time steps. So if we look back here, we're looking at, we want our time step to be bigger than this correlation function here, so that our operators will be independent of one another when we do the calculations. So that was it about correlation functions. So now we'll use them to get our dissipation rates for electron-phonon coupling and density matrix formalism. So the electron will be our system where we have it in some out of equilibrium state, relaxing, and it'll give energy to an ensemble of harmonic oscillators, which is represented by the lattice there. So first we start off with the Louisville equation and the second order perturbative correction. So this would be just our regular, this first term here would be just our regular Louisville equation, and the second term provides like our dissipation rates, or it's the second order perturbative correction. And then since we're only interested in the dynamics of the system, we can take the trace of the Louisville equation here, and we can basically integrate all the variables associated with the phonon, or the bath degrees of freedom. So that's what these trace operations here are representing. And this is like a general solution. We haven't made any assumptions about our potential and our density matrix yet. So the first assumption for the density matrix is that the heat bath will always be in equilibrium and that our system will change in time. So we can break our density matrix into the density of the system and then of the heat bath, which is always going to be at equilibrium times 0. And you can think about it as like if you jump into the Atlantic Ocean, right? Like you're not going to change the temperature of the ocean at all. You're going to give some energy to it, but it's still going to be like negative 40 degrees or whatever. Or I mean 40 degrees Celsius, not negative 40 degrees. Or 40 degrees Fahrenheit, I don't know. But you get the idea. And then the second assumption that we make is that our operators are independent of one another, or that we consider time steps larger than the correlation between the two operators. So f of t will be our heat bath operator in the interaction picture, which is what all that stuff represents, and then the system operator, which is qt. So if we apply those two assumptions and then do a bunch of simplification, we can get to this result here. So the Louisville part disappeared, and then we're just left with the dissipative parts. And we can see that it's generally two parts. So we have commuters that are associated with the system of operators in density matrix. Then we have correlation functions over here associated with the bath and the bath operators and bath density matrix. So from here, we can make this equation look a little bit nicer by doing a couple of manipulations. So we can turn all these commuter terms here into numbers. If we take the time dependence, because in the interaction picture we have the two exponentials there. So if we take two electronic states and then convolute the operator, we can get a matrix product there and then pull the time dependence out. And then what we do with that time dependence, we put it in with into the integral with the correlation function. And then we do a change of variables and change our integration limits to make the computations a little bit nicer. So we change our variables so that here we have two. They both depend on a parameter of time, but we can shift them or shift our origin. So one of them is stationary, and then the other one, we're just integrating over that variable. So t double prime, or t prime to t double prime, and then t to 0. And then we take our integration limit, we just go to infinity, because after a certain amount of time, we're just adding a bunch of zeros. So it's not going to change the value of the integral at all. So with those two approximations there, we get scalars or matrix elements out in front, and then we have the autocorrelation functions which provide our rates. Here we get two rates because we go back, we had a plus and a minus term here, so that's why we have a rate plus and a rate minus. And then skipping a couple of approximative steps here, we can use those rates, which they label as W, just summing the two rates together. But we can get changes in the occupation states of the density matrix. So time evolution of the matrix MM. MM represents a convolution between bra and ket M and M. So we get two terms here, which can be interpreted as states from N that go to M, and then states from M that go to other states. So it's basically the gain electrons coming to state M and then electrons leaving from state M, the state that you're considering. So then that's how we can use autocorrelation functions to get our rates for transitions between electronic states. So in summary, correlation functions are a pretty powerful tool that we can use to describe rates of transitions in our systems. And then the time evolution of the density matrix requires the Markov approximation so that we consider time steps larger than that the operators are correlated, so that we can get nice linear equations out of them. That should be it.
Okay, let's thank Aaron. Any questions?
You had an integral that early in the presentation that you went over the units that showed that it's a rate.
Yeah, so this one here, yeah.
Yeah.
So
H bar is 1 over energy seconds, right?
right, there should be another, because the reference that I use, they use gamma over H, so there's no H up here. So there should be an H there, so you get an H bar,
Yeah,
or 1
yeah.
over H bar, so you get H bar squared in the denominator here. So you get
How do you get it squared?
because it's easier if I just write that out.
Oh.
So if you have, so the source I used, they said K is equal to gamma over H bar. So then they go gamma I divided by H bar. Divided by H bar. So that's where the factor of H bar comes from.
I should say.
Huh?
Satisfied? Okay,
That's okay. I will look it up.
more questions.
It looks to me like the integral is over time. So the whole integral
itself is in units of energy.
Right, so
you
you
get
get-
energy
so this is
over
the energy.
energy seconds. So it's energy over energy seconds, which is 1/seconds, right? Which is great. I was just confused why I said it's energy seconds over energy squared seconds squared.
Do you oppose the final result? Or you oppose only the path?
Well, we get an energy times an energy, so joules squared times second.
Joules, but time is integrated over.
But we're integrating with time though, so that's where the seconds come from.
But after the integration, the seconds disappear.
No, you'd still have time there.
But it's integrated over.
Let's postpone this discussion to the actual class, and then we can come to the blackboard and find the ultimate truth.
Okay.
Other questions to the speaker? If more questions once, more questions two, more questions three. Let's thank Aaron once again. And the next presentation will be by Deyan Mikhaylov, who will tell us another aspect. So Aaron was showing what happens if the surrounding of the electronic system is in the thermal state, right? Deyan will show what will happen if the surrounding is the pulsed lasers. Same as we did for free induction decay and the photon echo, but he will tell more of the how to expand this approach to a more general situation.
Now I'm mostly concerned is how to expand this.
Hit the one that does all the whole screen. That one.
Just
no,
did that
that's
one.
one over. No, that's the wrong one. That's corner to corner. Next one over.
This one?
That one.
No,
No.
You can run PowerPoint and then
just take PowerPoint.
View. Presentation. Full screen. Where's presentation? There's usually a presentation thing.
Oh, full screen mode. That'll work.
Okay, so I recently had a kid. So, I mean, and I had a presentation at APS. So I thought both my kid and my presentation were beautiful. I remember this is a part of a three panel comic that I read once, but I couldn't find it. But I found this. The only difference is people never tell me that my kid is not beautiful, but people will tell me, but we will rip on my PowerPoint slides. Like this doesn't. I mean, you probably been to group meetings where Svetlana is present.
Oh yeah.
PowerPoint slides don't make any sense. Anyways,
you can share
same thing.
recordings with.
I mean, I appreciate every input on my presentations, positive or negative. The difference is you never hear, "Oh, that kid is ugly." You know, I never heard that, but maybe it's true. Anyways, so I'm going to try and make a connection between what we did in class and what is being done in spectroscopy measurements when people use double-sided Feynman diagrams. So in class we had what we call the block equation, which is for a two-level system.
But this is not block equation. This is just basic metrics.
This
Liouville equation.
This is Liouville equation. I've also heard it called block equation
No,
for
no.
the two-level system where you have a Rabbi frequency.
No, if you change the variables to projections of quasi-spin, like Sx, Sy, and Z, then it will work.
Okay. That clears. Anyways, so when we go to molecules, when you have many states and you have time dependence of your perturbation, then it is very difficult to construct this what's called Liouville superoperator. So one can benefit from perturbatively expanding the density matrix. So straight up expansion of the density matrix. Well, first, before we try to perturbatively expand it, we can just try straight up expansion. So this is like integration of the Liouville-von Neumann equation, where on the right hand side you have the time derivative of rho, and on the left hand side you have the time derivative of density. On the right hand side you have the commutator between the Hamiltonian and the density. But when you integrate over at different times, you get an equation like this. Right, but this is not practical, and it also, in many cases, it diverges. And even if it doesn't, converges very slowly, so it's very expensive. So before one goes to perturbation theory, one needs the interaction picture. So what is the interaction picture? Well, first let's remind ourselves of the Schrödinger picture, where one has a time-dependent wave function, and the operator is time-independent. And to compute the expectation value of an operator, you just take the inner product of the wave functions times the operator. So to get the wave functions as a function of time, one solves the Schrödinger equation. In the Heisenberg picture, you start out with your wave function at time equals t0, and you're not worried about how the wave function evolves in time. What you're worried about is, again, observables, which is expectation value of operators. So what you do is you solve the Heisenberg equation of motion, and you obtain the time dependence of your operators, and you solve for expectation value of your observables in terms of the stationary wave function and your time-dependent operator. So the interaction picture was kind of invented in order to deal with perturbations. So you have your state, time-dependent state, time-dependent wave function that evolves according to your full Hamiltonian, but you're interested in the time evolution of some other wave function called interaction picture wave function, and you're interested in time evolution according to the time evolution of the unperturbed Hamiltonian. So this wave function is kind of a measure of the difference between the full Hamiltonian, which includes the free and the interaction, and the free Hamiltonian. So this is a very useful quantity because it's known, the unperturbed Hamiltonian, and this is the time evolution. U0 is the time evolution according to the unperturbed Hamiltonian. So in any operator, any perturbation, time-dependent perturbation, can be expressed in terms of the interaction picture perturbation. Once this interaction picture operator, time evolution operator is introduced. So with this, you can expand the density matrix in terms of the interaction picture Hamiltonian, in terms of the perturbation in the interaction picture, which is known, your initial density matrix and your U0, which are also known because you know H0. So this is now at least doable. So this is the perturbative expansion of the density matrix, and this works. But now let's see exactly how it's implemented. So, for example, this perturbative expansion of the density matrix is used to compute polarization. One of the observables that is most conveniently computed this way. So polarization can be expanded in orders of the susceptibility. And when you take only the first one, we have linear optics. So the electric field depends linearly, the polarization depends linearly on the electric field. This one is usually omitted for several reasons, not only because of that one. This is one of the reasons why the second order is omitted. There are other ones out there. I'm afraid to make any claims. But the third order of the susceptibility is usually the lowest nonlinear term that's taken into account. In order to compute nonlinear polarization, you gotta take the expansion of the polarization to third order in order to compute it with this perturbative expansion. How is this related to density matrix that we just saw on the previous slide? Well, any observable is can be computed from the trace of the density matrix. Any observable that depends on statistical ensemble can be computed with density matrix. Which wave functions can't give you statistical ensemble, but density matrix can. So the polarization is the trace of this dipole operator times the density matrix. So plug this in, one gets an expression for the polarization in terms of the time-dependent electric field, and this dipole operator that only depends on intermediate times. And when you make the substitution from Schrodinger, from interaction back to Schrodinger picture, these time evolution operators that we saw on this slide, they disappear, because now here you get a u dagger times u, which is 1, and here you get u dagger not times u, which is also 1. So one is left with evaluating something like this, or this inner product. So for to the third order regime, one has commutator mu naught rho t naught, and then mu naught with whatever this is, and then mu t1 plus t2 plus t1 with whatever this is. So you have a product of 3 commutators, which is 2 times 2 times 2, which is 8 terms. So I went through the pain of typing them all up, and you can see that mu t3 plus t2 plus t1, which is the latest, mu doesn't really come into effect because it's not inside the commutators. But in here we have all 8 possibilities of expanding these brackets that we end up from the commutators. So what you do is you number the terms, and to keep track of the terms, Feynman, a long time ago, developed his diagrammatic technique, where you draw a line of that represents your system that flows in time. At every time you have a perturbation, you have a vertex, after which you have some new momentum, before which you have the initial momentum, and your final momentum is your initial minus the momentum of your perturbation. So you have momentum conservation. There are many rules of how Feynman diagrams are constructed, but what they do is they help you keep track of all these terms that you get. So for example, before you go and calculate all these terms, you can draw your Feynman diagrams and see which ones are relevant. And so for example, diagrams like this one will give no contribution, because a pulse has to leave the system. So you can think of this as sending a pulse into the system, waiting a little bit, pulse comes out, sending a pulse into the system, waiting a little bit, and pulse comes out. Also diagrams where, for example, 3 pulses leave and 2 pulses come in will also give 0 contributions. This is relevant in pump probe spectroscopy, where you send a short. Another important thing to mention here is that these pulses have to be so short that their times don't overlap. And then you can do things like time ordering and rotating wave, which are big approximations that significantly simplify the number of terms involved. Yeah, photon echo and pump. Photon echo is what's is a phenomenon that can be calculated with this technique, and that's what's that's the phenomenon that's prevalent in experiments like pump probe spectroscopy, as far as I understand.
Okay, let's thank Deyan. Let's move. Maybe someone has questions to you.
Yeah.
So for those little squiggly arrows, like what does it represent that, like the directionality, like if it's going right or left?
If it's going right, it's the sign of the electromagnetic wave. So you have e to the power of negative I kx plus omega t. If it's going one way, you have e to the plus I kx minus omega t. If it's going the other way.
So it's like different phases?
So it's different. No, the phase is. I'm not sure how the phase will come in here, but it's just the propagation. E to the ikx plus omega t tells you which way the wave is traveling, if it's going left or right. And the way they do experiments is they only look at a certain direction, like the transverse direction in the material, for example, or so you can only have a wave coming in or a wave coming out. So you have to what they do is they very carefully set up their experiment so that you can only look at 2 directions of the wave, as far as I understand, yeah. And you only work with a certain polarization. I think you only work with circularly polarized light. So you can.
Is that kind of like convention, or is it just?
You have to ask an experimentalist who does pump probe spectroscopy what they do in order to simplify what they're looking at. And please help on this question.
Let's discuss it later. It's a serious question.
It is a serious question. But mathematically speaking, yes, if it goes right, it's e to the negative I kx plus omega t plus I omega t. If it's going left, it's e to the minus. If it's e to the plus. Yes, the sign of the electromagnetic wave. That's what I read in the book. That's authority on this.
More questions?
How it's implemented is.
Deyan?
What's the down and up mean on the vertical lines?
The down and up on the vertical lines is my fault in taking out these arrows. The arrows on these lines don't mean anything. Both of these lines propagate in time. So both of these lines you can think of as the propagator.
What we hope,
yeah.
and you will correct me if I will be wrong.
Okay.
So we all agree with wave function that can evolve in time, and this line is wave function going forward in time, forward, minus infinity plus infinity time. But now for observables, we need not only wave function but wave function conjugate, and we propagate them together in form of density matrix. Instead of bra and cat, we have cat and bra. So we both cat and bra. So conjugate of wave function is the second line, which is propagated also in the same direction, but it is wave function with star conjugate. And then we have the same time slices. So at this time, pulse comes in, but it affects only
The kid.
cat and doesn't affect bra. Then we wait, like some other diagram, like here, wait, at this point, pulse affects bra. And if one takes all these processes into account, then one gets realistic observables. Yeah? Any objections?
No, that's perfectly valid from a mathematical standpoint. I was trying to physically explain what the lines actually mean. It's propagation of density matrix, if you want to think of it that way. It's kind of abstract. Doesn't in single-sided Feynman diagrams, these mean actual particle propagating through the system. But here it's like the statistical average of a.
Satisfied? Question that maybe as a homework, draw a diagram for photon echo. But now we do not have time. Just make a piece of paper with diagram for photon echo. Okay, let's thank Deyan once again. And the next presenter is Brandon Gifford. So he will open our eyes broader. He will show that all techniques that Deyan has introduced are applicable not only to photons, but also for radio frequency pulses. So he will look more on the physical implementation and analysis of the processes, but it will be same nature of multi-pulse experiment, bringing, creating coherences and then letting them to relax and connecting it to a real world and observables. Floor is yours.
Okay. Okay, so we talked about NMR a couple of times thus far, and I think we've, when I talked about it, I put it into the context of continuous wave experiments. So there we're thinking about a nucleus, right? It's got spin and it's wobbling. And when that so then you shine that sample with an external electromagnetic field, and when the external electromagnetic field's frequency matches that wobble, you see resonance, and if you can determine those frequencies, then you can determine something about that wobble, which will tell about the local environment of the electrons. I'm sorry, of the nucleus. So instead of doing continuous wave experiments, though, in reality, they're doing FID experiments, which are free induction decay. So in this method, you're getting the same data, but what you're doing is you're first taking your sample and you're making it all resonate, right? So all of the nuclei in the sample are made resonate at once by shooting it with an electromagnetic pulse, very, very short electromagnetic pulse, and then that short electromagnetic pulse makes them all resonate, and then you can watch it over time and determine the times at which they resonate back, if you will, and then that'll tell you some information about the local environment of the electrons by telling you the energy or the frequencies with which these wobbles occur. And so this is in reality how they do it, because you can do it very quickly. And so even though the signal to noise ratio in this method is more, they can do, because it's quick, they can do lots and lots and lots of runs and then average them. Okay, so just to show a little bit about the instrumentation, so they have the magnetic, or the magnet, which we talked about before, and your sample. And so the important thing here that I guess I want to get across is, so you have the receiver, which is getting the, which is showing, or which is telling us when they, or giving a signal as to when they resonate back over time, right? Because then they're outputting energy. But then you also have the input, so the input electromagnetic frequency, and so they actually mix these two. And then by reading that profile that they get, which I'll show you in a minute, then that's where they can do their Fourier transform and determine the waves that are coming out here from the receiver. Okay, so actually I'll talk about that first. Okay, so here's some real life signals. So as I just mentioned, you're going to see this decay over time, right? Because you actually made all of the sample resonate, but then also you're going to add in the RF frequency that is incoming. And so by reading the distance between these waves, how we can determine the amount of time with which they relax. And so if this complex, complex waveform, a sum of waves, we can see that like in this example where it's going, where there's the broader wave, which corresponds to the 1 second signal, and then the finer wave, which corresponds to the 10 hertz signal. I'm sorry, 1 hertz and 10 hertz signals. And so again, if you do a Fourier transform of this, you can deconstruct which waves existed in the original sample. And so in order to actually invoke this experiment, then we're going to be making a 90-degree pulse, which means you're taking all of the spins and taking them from there to this plane. And so now they went from the z to the xy plane. And so now you can imagine this vector, this wobbling, or not wobbling, but turning around in the plane. And so they're a little bit offset because, as we mentioned, their local environments are slightly different. And so then after a brief time, so what we'll do then is we'll give another pulse. And so that's a 180-degree pulse. So then now flip it back to the opposite side of this plane. And then we are able to see when they come back together, because then we get a spin echo generated at that point. And so then, so that will tell us, or so then we're actually doing multiple pulses, and you get the signal after the second pulse, right? Then you're actually reading the echo off of that signal. And so if we imagine it in the 2D plane, which I just described, so we have the x and the y. So if the singlet, and meaning that there's just one signal in the mixture, then you would have, then you just have one peak, right? But if you have, say, two signals that are in the mixture, and again they're at slightly different angles, they're going to be dependent on each other. So you would then be able to, read the degree to which they lie in the x and y plane at one point, or correlate the signal to that. And so the signal looks like this, and so for correlated electrons, then you get signals that look like this, where they can go up and down, and then you have then that tells you the degree to which they're lying in the xy plane when they resonate. And so then triplets and quartets look like this. So I guess the important thing here is that by reading this, they can determine if you have two individual singlets, which means two signals from non-coupled nuclei, or you have signals from coupled nuclei. In that, then you get this more complex signal. And so, as I mentioned, they're reading it after the second pulse. And so by reading the second pulse I should mention, so these different profiles then too are over time. So at time equals 0, everything's up, right? But then as time goes on, you get a slightly different signal. And in the case of the non-coupled systems, that's not true. But in the case where they're coupled, then you get the signal where it's down. You get a reading over time as we go from this to this to this to this, etc. And so if we were to change the time that we read after the pulse, or after the second pulse, then we can get multiple of these profiles where each one looks slightly different. So the normal spectrum, again, would be this, say, time would be here, like this, what called time equals 0. In other words, read at the echo point. So you do the second pulse and then read when you see the echo. And then if you start to read later than that, you get this signal and then read a little later. Again, you're changing the time after which you read. And then if we want, we can take these spectra and we lay them onto 2 dimensions. But just by shifting each of these. And then, by both doing a normal NMR experiment, but by delaying the time between the first and second, or between the second pulse and the read, we can get some information as to which signals are coupled to which signals. So, for example, in this case, of course, all the diagonal signals are coupled because they are themselves. But then the off-diagonal signals, you'll get a point at which, or a point for coupled signals. For example, this signal and that signal are coupled, meaning that in a chemical sample, those nuclei are close together. Or say here, there is no signal, so we know that signal and that signal are not coupled. So whatever nucleus or nuclear environment is creating those signals isn't coupled to each other. And so there's a number of different experiments where they do it in this way. And so one is COSY, which is homonuclear, meaning you just do hydrogen, and then you can determine the chemical, or you can determine which hydrogens are close to each other. But if you want, you can do heteronuclear, which like HETCOR, where you do carbon and hydrogen. And so then you end up determining which hydrogens are connected to which hydrogens, and NOSI, which is different. All right. I think that's it.
Okay, thank you. Any questions you wanted to ask?
I missed how you. So you run NMR and you want to know what's in your sample, right?
Yes.
I thought, okay, so don't you need like some data from like beforehand?
No.
Be like, oh, this P corresponds to a methyl group, this ethyl group, this.
Yeah, you do have generally known tables. So, for example, in this, if it's between like 1.5 and it'd actually be 0 to 1.5 ppm. Generally, is the methyl group or methyl groups which are connected to nothing else, or the hydrogen's connected just to a carbon in the methyl group. And then the more electronegative the environment gets, you get further and further. They call downfield. And so then you have charts which say if it's in this range, then it's probably connected to something else. So for example, things way up here above, I think 7 ppm are connected to nitrogen, hydrogens, etc. And then in this range, it's a bunch of different sp2 hybridized things and ethers and esters where they're connected to an oxygen that isn't an alcohol. But yeah, but then I think the more important part actually is the splitting when you actually read the NMR. The more important part is the splitting because that tells you what things are adjacent. So it's not only important to know what it's connected to, but also how do things split. So if you have a sample and you have nuclei in a local environment that are going to resonate at a certain frequency, if their environment is similar, then they're going to resonate at a similar frequency. So if you were to look at one, you could have either the adjacent one up, contributing to the magnetic field, or down, opposing the magnetic field. So the environment that this one sees is dependent on the environment, or on how this one resonates. So then they'd have to be close in frequency in order to get that coupling.
More questions? If not, let's thank Brennan
No?
once again.
Oh, thank you.
So, by now, the information that we are getting is not yet sufficient for immediately diving into this research area, but at least it does show us a pathway that we are getting new dimensions and new skills to characterize behavior of quantum systems from different angles. So if we do have an opportunity to follow the phase of superpositional state, to create and to read them by short pulses and see how they evolve in time, so all the skills open us a door into a new popular application of modern days, so-called quantum computers. So it is so popular that there are 2 volunteers there were more than 2 who wanted to present this. So Samuel Brown will start, and then there will be another talk on this subject. Forde, yours.
Thank you. Yep, so I'll be talking about quantum computers. Just kind of an origin. So we all have heard of Moore's law, where the number of processors on a chip increases exponentially with time. So that's Moore's law. Here's just kind of an example of that. But at some point, this is going to reach a limit due to size restrictions and quantum effects, just as you're getting smaller and smaller within the chip. Richard Feynman in 1982 proposed putting quantum mechanical effects hardware into these computers to make quantum computers. And then David Deutsch came up with a theoretical paper proving the probability or giving how this could actually work. So like with a quantum challenging or a problem with a quantum computer can solve is something that has like the number of processors or the degrees of freedom increases exponentially within. So the challenge as the size increases exponentially increases. So that's where we want to start to use quantum computers, because our classical computers don't work with these very well because they don't increase nearly as quickly. So a qubit, we all know that these can be a superposition. So here's just a block diagram where that qubit can be either the 1 or the 0 state or any superposition in that. And this allows us to have the superposition to have many different states. So let's just move on. So we have the wave function for this, where C0 and C1 can be represented here, and this is supposed to be theta. And that's our single qubit. So when we have these qubits, we want to be able to manipulate them like in a regular computer. So regular computer has logic gates, so you have a input 1 or 0, and when it goes through the logic gate, it becomes either 0 or 1 depending on what it was and what that gate is. So like in a NOT gate here, you have these truth tables. So this A comes in, if it's a 0, then it just switches to the 1. So that's our typical classical computer, and there's several of these which I don't know many more of them. They're not the easiest, just switches signs. So we're going to try to look at these from like a computation or a quantum gates. So in the same way, we want to have an input qubit with a wave function here with the different coefficients, and that goes through our single qubit gate, and that comes out with a different wave function. So here I showed the NOT gate. On the other hand, here are some typical logic gates for a quantum system. So we have a NOT gate or an X gate, a Z gate, and then a Hadamard gate, H gate. So here's the matrix form of these different gates and how they'll operate on the matrix form of that operator or on the wave function. So here's our wave function again, and if we're in this state, in the 0 state, this is our wave function in matrix form. And then if we operate on this with the NOT gate, we get it to switch going up. And so we can do this with the Z gate, the same thing. So in this case, we're in the 1 state, and doing this with the Z gate, we get another switch. And then the Hadamard gate, we can apply these to get different states within our system and can kind of control the states. Then there's the combined gate, the C0 gate, which I don't exactly know how, but apparently with this gate and the like 3 other gates, those are like the primary things that you need to start making different things within your, like these are the basis of what you need to build up for a quantum computer. So here's the C0 operator function, and then the what it does is it has a control and a target. So it looks at the control, and the control never changes. So here's the control will always stay the same in these inputs. So the control and the target. So the control doesn't change throughout these, but it looks at the control and then changes the target gate. So if the control is in the 1, then it'll flip the target gate. So we'll just kind of go over a quick example of changing a state that's in the 0th state, where we have the Hamadre operator, and then going into that C0 gate. So if we first have a state within the 0th state, we apply the Hamadre one here, which is this function. We get these 2 states, or the wave function in this state with the 2 different coefficients. And then we multiply again the 0 state here to these 2, which gives us this state. And and then we can apply our the C0 gate, which I showed in the previous slide, which is here, to this state, which is right here. And then we can get a flip of this state. So this is our out. With this, there's applications. So here's just a few different applications to some quantum systems that can actually be used, like a quantum dot. People have used it. You can flip between the excited and ground state. Photons, I think, can change with the polarization between horizontal, vertical. So a couple examples of how these can be used practically. And then any questions?
Thanks, Sam. Any questions to this to the presenter on this hot topic?
Oh, what's a qubit made of?
Yeah, so that's like the challenge and such. This is a few examples of where you could try to make them, like maybe with a quantum dot or something like that. I think I saw there's like a nitrogen vacancy. That's how you can try to get, because you just want to be able to control that thing with the external.
I've seen things like vacancies.
And that nitrogen vacancy, I think they have like diamond and they put in nitrogen of like ion implantation or something, and then they can get it. So you're just trying to control the wave function of something separately. I think there's challenges in trying to get them to be close enough to where they have coherence, and like practical applications, which I'm not in the field to know enough about what the practical applications are and such. And like they want it to be like room temperature. Like that's the goal, have it room temperature where you don't have to worry about it as much.
So they'll get 2-level atom?
You want a 2-level system, 2-level atom, something like that.
Okay.
More questions? Let's go to slide number 3, where you show 4 plus 5. So why 0, 1, 0, 1 equals 5? Or let's make a verbal quiz. So let's give a problem to Sam and he will solve it just from the top of his head. So let's suppose that you have record 3 qubits and they all are in the state 1. So 1, 1, 1. How to convert it into decimal? Which number will it be?
Is this a binary or is that
convert 1, 1, 1 from binary code to decimal.
It's been such a long time.
Anyone wants to help you?
I think I know. 7.
Yes! Very good, very good. So can you explain to Sam how did you do it?
Yeah, so the left or the rightmost run is the 1 spot, and then the next one is 2s, and then you just double it from there every time. So the next one is 4s. So like in our system, you know, the first one's 1s, and then it's 10s, and then it's 100s. Binary, it's the first one's 1s, and then it's 2s, and it's 4s, and it's 8s, etc. So I just did 1, 1, 1, just 1, 1, plus 1, 2, plus 1, 4.
So 1 plus 2 plus 4 equals 7. Good. Let's go to the slide number 9 with control note. Multiple choice quiz orally. And I invite everyone in the class to help if that we do it quicker. So the conversion operator that corresponds to going from 2 qubits in initial state to qubits in final state is represented at best by one of the 3 mathematical concepts. Choose one. Hamiltonian, evolution operator, Liouvillean. Which one?
I'll go C.
Any other options? How do we go forward from the past to the future? Not infinitesimal, the longer times. Hamiltonian, Liouvillean, or evolution operator? Yes, yes. So the evolution operator that would physically represent this gate should look this way in the matrix representation. So it's not Hamiltonian. It's not Liouvillean, it's evolution operator. Good. More questions to Sam? If no, let's thank him once again. And last but not least, very important presentation by Levi Lustrom, and he will increase our knowledge in the aspect that was inducing the interest of the audience. So Deyan was asking, what is the qubit? Or we were recently discussing which mathematical construction corresponds to implementation of the quantum gate. So Levi will review from his angle basics of quantum computing, and then will give an exact, explicit example how to implement this 2-qubit gate and how it works in details. Floor is yours.
So the beginning will be very similar to Sam's. So classic bit, we can do ones or zeros, so it's not that, and we have to have the same number of bits as we do the numbers, but if we go to quantum bits, if we have a 1 bit, then we still get 1 or 0, some linear combination, which is not as important. But as we increase the number of qubits, the number that we can get goes much quicker, because we can get 0, 0, 1, 0, and so forth. And then, so if we go to 3, then we get 8 combinations, which is very preferred, and they're all linear combinations. And then they're orthonormal. So this is another representation. So we can do like C1, C2, which these are just the coefficients, and we can see that they grow rather quickly. So as Sam did, we can project it onto the block sphere, and then what's important is this quantum gate, because we go with all of our states and then we want to change them. So Sam talked about both of these already. So there's the single gate and the multiple gate, the 2 gate. So I'm not going to explain that again. So getting kind of into application, if we look at the like the sphere, and we want to go from state 1 to state 0, we can use the pulse area theorem to go from top to bottom, and we could do like a pi pulse or a half pulse, which would get us on both sides. So this is kind of the example. So if we have a system that has both down and then both up, we can get 2 intermediate states where we have the first system is up, the second system's down, and then we can do another intermediate which is the opposite, and then the top which is up, which is important. We want to have a slight difference here and here, so when we do different pulses at different energies, then we will occupy a state or deoccupy it. So going from 0, 0 is obviously nothing, but we can look at this where we go from 1, 0 up to 1, 1, and we would do a pi pulse at the energy that they say is omega A, so then we go from 0 down. But if you look at this, we would just do a pulse at omega B, so then we go from 0 to 1. So if we look here, we would go from 0 at this energy, so it only affects the second stage. And we go from 0, and then we do a pulse, and then we go up. So we can use, if these energies are correct alignment, so we don't get overlap, then we can easily do the 4 different states, and then that will give us our logic gate. And we can say, if we want to go from 0, 0 up to 1, 1, we have to do a full pi pulse at both A and B. So in conclusion, quantum gates are much better. They can be on the block sphere, and then we can set up a correct system where the energy levels are finite so that they don't overlap. So we can do pi pulses to get different levels. And one example that a paper had was like a quantum dot, and then they're embedded so that you can shine different quantum dots with lasers, and then you can have a detector, and then that can be your qubit. Any questions?
Let's thank Levi for being extremely efficient in this complicated subject, and the presentation is open for discussion. Jaynes?
How would you read that quantum bit?
What?
How would you read that information from this?
Perfect question.
That I'm not. I guess I would intuitively think about like spins. So if you had spins, then you could look at the magnetic field, because up spin
Then
and
it
down.
will be changed.
What?
Then if you apply the magnetic field, that can change the spin of the system, right?
If you use something like a flux, so not applying a field, but just detecting a field. That's maybe one way. The quantum dots may be a bit harder to do it. I didn't look into how to detect it that much.
But what is your instinct or intuition? If you have spectroscopic quantum system and it is either in one or another excited state, how would you read in which state it is?
You could maybe shine, no, but then if you shine a light, then you ruin the system.
But do not restrict yourself, just unleash the imagination.
I guess if we're in like 1-1 and we shine this amount of light, then we know that we're in this state because that's the only state that has that light.
So you mean spontaneous, or not spontaneous, induced emission?
Sure. So.
Or maybe something similar to the echo, that photon echo that keeps track of the phase, and this depends on the phase and superposition.
Because all of these have different energies, right? So if we say we do a pi pulse on like omega A, then if it's absorbed, then that will say it's in a specific state. But if it's not, then it's in a different state for the first and second, the first qubit. So then you can do a pi pulse at B, and that will tell you which state both of them are in. And then you could follow it up with a second pi pulse in both energies, because then you will revert back to the initial state. But that would be my guess, I guess.
So how many lasers do you need to implement this gate?
Probably 4.
Okay, good. So now another question to you as to growing quantum chemist.
Okay.
Why 1-1 state has energy that is different from omega A plus omega B? Just in real life, not related to quantum computers, but based on your quantum chemistry research and background.
I would say they might be interacting, and that energy of interaction will raise it.
Yeah, it could be either increasing or decreasing, but like Coulombic interaction or.
Yeah.
Okay. More questions to Levi?
How do you store things in memory in quantum?
That's the speaker.
I always wondered that. I can probably just look it up, but I'm late.
Let me reformulate. Are you aware of availability of long-term storage for quantum computing, or everything should be done really quick?
I would say, from what I have read and my take on it. This is more the processor, not the storage.
Yeah.
So if you want to store it, you're not going to store it in the processor itself. You're going to store it in RAM or something else. So this is for the calculations, if that makes sense.
Yeah.
So the storage time is limited by the time of reinduction decay. Everything, processing, reading, storing should be done before it happens. Really quick.
Which
Otherwise,
is a benefit for if you're doing processes, because you want it to be quick, quick, quick. You don't want to have to wait a long time. Maybe saving the data will have a bottleneck, and then it will get ruined. But I don't know of any way to store on the system.
So you use classical computers to store, quantum computers to
compute. There may be technical issues, but I didn't read into technical. It's still in its infancy, I would say. So there's a lot of questions.
That actually was one of my questions now.
What?
So like a couple of years ago when I was thought this stuff might be cool and I was looking it up, they still were at the phase of only having done like a couple of bits for millions of dollars. I think it was still all just completely prototype. Has anything changed or?
I didn't look into the real implementation, like real world.
There's supposedly a company called like the D-Wave or something that's got their own one, and it just kind of popped up out of nowhere in Canada or something like that.
So like it's a fully assembled computer?
It's huge. It's like a supercomputer, and they use like a super cooled type of thing for the quantum system.
And I think it has to be at like almost 0 Kelvin.
Yeah, it's very cool. But I think it has. They claim it does.
so which physical principle do they use?
I'm not sure.
Sam was listing like 6 possible implementations. So which of them are possible? Which of them are closer to commercialization?
I don't think any of them are close to commercialization.
Spin, polarization, excited state. You didn't mention the ultra-cold atoms, which may fall into one of this excited state, but it is a little different principle. When magnetic fields trap ions in vacuum, so they do not touch anything, and then the lifetime of excited state is a little longer than for other implementations. Okay, well, many thanks to Levi for presenting and supporting the discussion. So, with this, I would like to thank all presenters who covered all these interesting subjects. So, let's meet a couple of times more this week. Wednesday, 6 p.m. in the lab, and Thursday at noon at this room. And the next week there will be another conference that some of us are traveling to. So there will be another silent period. Okay, thank you and see you tomorrow at 6. Meeting is dismissed, and I'll stay here just in case some of you have questions.
So this is